So the next set of circuits we're going to talk about are inductor circuits. And whereas capacitor circuits stored electric fields, so you can think of them as doing work to store energy, inductor circuits store magnetic field. And they do this directly with the fact that it's essentially a circular loop around the circuit. You can kind of think of it as a solenoid. As the current travels around in that circular motion, the magnetic field, using the right-hand rule, gets kind of stored inside the solenoid going the same direction. So the unit we use to measure inductance is in Henry, and because oftentimes they're small when dealing with circuits, we're going to be using millihenry specifically. So we're going to look at millihenries, and that's going to denote a little m and a big capital H. The same is true for, so we're going to look at specifically first an inductor circuit that's in series. If we're attaching it to a power source, as it's attached to the power source, you can think of the inductors as charging up, and they will store energy even once the power source has been removed. So for this case, voltage for the series, it adds still. So we're going to call this, for the series of inductors, it adds across the entire circuit, just like it has on our previous examples of the capacitor and the resistor circuits. The inductance also adds. So the equivalent inductance or total inductance is going to just be the sum of all the inductors for the series of inductors. And the current, in this case, when we talk about inductor circuits, we are not just talking about current. We're also talking about change in current over time. So the current stays the same, and the change in current over time, the I dt, also stays the same. So I maybe specify that it's not current. I mean current as in it's constant. I wrote current. It's constant. And the same with the change in current over the change in time. It's also constant. Now you might think if current is constant, then wouldn't di dt be 0? Each inductor is storing current at a specific rate. So they don't equate to each other. I is constant and di dt can also be constant and not 0. So the voltage, so the few equations we're going to look at. The one specific for inductor circuits is that the voltage is equal to the inductance times the change in current due to time. Okay. Oftentimes you might have also seen a negative sign here. I'm going to represent this equation without the negative sign. All that negative sign is saying in which direction the current is being stored. So in terms of the inductance, it resists the motion, which is why the negative sign is there. As we look across each individual inductor, though, we just need to remember that that is directional. So we don't have to write it for this case. We're also going to use that the total voltage, again, since it adds across the circuit, is equal to the sum of all the voltages across each one added up collectively. So we're going to first figure out the total inductance. So the equivalent inductance or total inductance is equal to L1 plus L2 plus L3. And in this case, that's the 10 millihenries plus 11 millihenries plus 12 millihenries, which we get that the total inductance then is 33 millihenries. So before I do anything further, because I know that this is an in-series circuit, the current is constant across the entire circuit. So this is also 10 amps. That's an I. And it's 10 amps across the entire circuit. So I'm going to be using the equation V equals L di dt, and I'm going to be using this to solve for time. So the first thing I'm going to do is get di dt by itself. So that's equal to voltage across the inductance. And then I'm going to integrate both sides with respect to time. And what happens to the left side is it becomes the current in terms of time, so some function of time, which is then equivalent to V over L times T. Now you might be saying, because this is an improper integral, do I have to include a constant there, so plus c, because it's not bounded? And I don't, because before I hook it up to the battery, there is no initial current. So my initial current is 0. So I could say plus c, but c is just 0, so I don't need to include it. So in order to find time now, I can just get time by itself. So time is then equal to the current at each specific instance, which in this case for a series set of inductors is the same across the entire circuit, divided by the voltage over the inductance, which another way I can do that to get the fraction out of the denominator is I multiply by the reciprocal, so it's the inductance over the voltage. In this case, I've got my 10 amps multiplying to it my inductance, which is 33 times 10 to the negative 3 henries. I'm not going to want to keep that in millihenries. I want to keep it in henries in order to convert to seconds for my time, divided by the voltage, which is 20 volts. When I plug that into my calculator, I get 0.0165 seconds, or I could rewrite that as 16.5 milliseconds. So I can say that this is 16.5 milliseconds. And that is going to be the time across the entire circuit. What does that mean? That means that that's the time it takes for the circuit to get to a current of 10 amps. Because I have introduced inductors, it's not going to happen instantaneously. The inductor will oppose that current. So it takes time to build up the current. So it takes 16.5 milliseconds across the entire circuit. So you could think of the time as being constant. That's not exactly what's going on here. You can just kind of think of, in tandem, the entire circuit is taking that long to build to 10 amps. So the voltage equals the inductance times di dt, which I'm just going to write like this. It's just the current over the time, right? Especially if I'm considering my initial starting points to be 0 after I've integrated it, right? So in terms of this function right here. I'm then going to look at, all right, I want to figure out the voltage across 1. So V1 is equal to the inductance across 1 times the current across 1, which is just the total current, times the change in time across 1, which again is just the total overall change in time it takes to build up to that current. So this is then going to be 10 times 10 to the, times 10 to the 3. So 10 times 10 to the negative 3 henries, multiplied by my current, which is 10 amps, divided by my time, which is, I'm going to rewrite as 0.0165 seconds, or you could do 16.5 times 10 to the 3. It'd come to the same thing. Roughly about 6.06 volts. I can then do the same thing to figure out the voltage across 2. So 0.06 volts. The voltage across 2 then is going to be V2 equaling L2 I2 over T2, which in this case is going to be the 11 times 10 to the negative 3, running out of space here, but 10 amps over, we're going to say 0.0165 seconds. When I plug that into my calculator, I get that V2 is roughly about 6.66 volts, something like that. And then I could either use the exact same equation to find the voltage across 3, or I could note that the total voltage is the sum of all the voltages, the voltage across 1, the voltage across 2, and the voltage across 3. So either way, across 3 is equal to 7.27 volts, roughly. And again, there might be some minor discrepancies when you plug these into your calculator. That's just based on rounding, because we're dealing with really, really small times, and the inductance is small, right? So the units are small, and the discrepancies just have to do with the significant figures we chose to round. Now let's look at if we have an inductor circuit where the inductors are in parallel. So this, in this case, we know that the voltage is constant, right? So voltage is constant. We know current adds across a parallel circuit. For inductance, the total or equivalent inductance is the inverse sum of the inverses, just kind of like we did almost in tandem with resistors. So in this case, it's the inverse of 1 plus the inverse of 2, plus the inverse of 3. And all of that is also inversed. Make sure that we know that that is -1. For this case, I am going to then look at, well, how is the change in current affected over the entire circuit? The change in current, so dI dt is not constant, and it doesn't directly add. It adds in relationship to how the current changes. So we're going to say it's proportional to the current. Okay, right? Another way we write that is this funky little symbol right here, to the current. So it's proportional to how the current is changing. So we're going to look at this with some specific examples to calculate total inductance and also the amount of time it's going to take for the current to charge up to 10 amps. So we'll walk through what each of them means, but let's look at equivalent inductance, or the total inductance, right? So the overall inductance of the circuit itself. So again, inverse sum of the inverses, right? So this is going to be 10 to the -1. I don't need to unit convert here since I'm looking for inductance. All my units are the same. I can add them without having to convert millihenries to henries. I'm going to do the conversion later, but the answer I'm going to get for total equivalent inductance is going to be in millihenries. So that's 10 to the -1 plus 11 to the -1 plus 12 to the -1, and all of that is inversed. What I get is 3.65 millihenries. And using the same equation that we did before, after integrating to figure out current and time, we found that I as a function of time is then equal to the voltage divided by the inductance times the time, right? And in that case, we can resolve for time. Time is then equal to the current, and in this case, it's multiplied by the inductance over the voltage. And we can plug this directly in again just to find essentially the time it's going to take to get to 10 amps, right? So it's going to equal 10 amps times our inductance of 3.65 times 10 to the -3. Here's where I need to convert to henries. And that's divided by 20 volts. So my time is equal 1.8 milliseconds. Now this 1.8 milliseconds is the time it takes for the current to completely charge across the circuit. That means that every single time across each of the inductors is going to take 1.8 milliseconds. 1.8 milliseconds. And the current's not going to be the same. So each inductor is going to work differently in terms of how it fills that current, but across all the inductors, in order for it to complete the full amount of current, is going to take 1.8 milliseconds. So you can think of them as working simultaneously together to build up that charge. So another thing we know is in parallel, voltage is the same. It stays constant. So this is 20 volts. This is also 20 volts and 20 volts. And then the current adds. So in order to essentially solve for the current, we're going to use our same equation really in this format right here. But we're going to essentially just keep it like it is and solve for each of the individual varying currents. We get that the current across 1 is equal to the voltage across 1 divided by the inductance across 1 times the time across 1, which is again the same time for every case. So as the voltage, could treat those as a constant and then just plug in different inductances to see how it changes. But this one we get 20 volts over inductance has to be in henries, so it's 10 times 10 to the -3 henries. Then I'm going to multiply that by 1.8 times 10 to the -3 seconds. So henries and seconds. We have to have the correct unit. It's something like 3.6 amps. 3.6 amps. We can do the same thing with I2 equaling V2 over L2 T2. I get 20 volts over 11 times 10 to the -3 Henry times 1.8 times 10 to the -3 seconds. Plugging into my calculator, I get that it's something like 3.27 amps, roughly. And then I can find the last current by either just knowing that the sum, so the sum of the currents, the current total, equals the sum of the currents. So I can take 10 minus 3.6 minus 3.27, or I could use the same exact equation to figure it out. You should get something around like 3 or 3.12 amps. So it's just smaller across it, and that'll sum up to 10. So as the other examples we looked at for the resistor circuits and the inductor circuits, we're going to look at, and capacitor circuits, sorry. We're going to look at inductor circuits where we have a combination of both in series and parallel inductors, and what that's going to look like. So to start, we're going to essentially want to derive our equivalent or total inductance. So L total, or L equivalence, is going to be, if I think about the in series as the sum, and the in parallel is the inverse sum of the inverse. So it's going to be L1 plus, and then now I'm going to do this inverse combination in here, right? So it's the inverse sum of this whole nasty thing right here. So that's going to look like L2 inverse plus the inverse combination of L3, 4. And since L3, 4 are in series, those just add. So I'm going to set another little parenthesis in here saying L3 plus L4 inverse. And that's going to be my total inductance. And before I start plugging in numbers, let's just get all our algebraic equations written down first. Let's now look at the total current over this entire circuit. The total current over this entire circuit, total or equivalent current, right, is going to, it's the same, it's constant in series, right? So it's going to equal I1. It hasn't changed at all there. But then that is going to equal the sum of the parallel. So that's the sum of L2 plus L3, 4. And if we remember, so L3 and L4 are in series, so those should be the same. So we can write it in one of two ways. We could write it as I2 plus I3, or we could write it as I2 plus I4. We could just denote too that I3 is equal to I4, so it doesn't really matter which one we put there because they're the same. And then the total voltage adds across in series and is the same in parallel. So it's going to be V1 plus, if it's the same in parallel, then it's going to equal V1 plus V2. Because V2, it doesn't change once it's in that parallel. So it's V2. But V2 is going to equal this V3, 4 combo, which is in series, so that adds across it. So it's going to be V3 plus V4. And now that we have a system of equations, we also remember that V equals L di dt, and that we, after integrating, we know that I as a function of t is equal to V over L times t. We can then essentially evaluate the rest of our unknowns. So let's start by finding our total inductance, and then we can calculate the amount of time it's going to take for the current to charge over this entire circuit. So let's look at V, or L total, is equal to L1. So all of these have to be, in this case, when I'm looking for equivalent inductance, I don't need to convert to Henry. I can keep them in millihenry. So I'm looking at 10 plus essentially 11 inverse. So you could write it like this, or you could just write 1 over 11. It's the same thing. But then I'm going to do 12 plus 13. That's to the negative 1. All of that is to the negative 1. And I get that it's roughly, when I calculate it and round, something like 17.64 millihenry. So 17.64 millihenry. And then I can now use this total inductance to calculate the amount of time it's going to take to charge to 10 amps. So I'm essentially going to rewrite this equation here in terms of time, right? So we know time is then equal to my current as a function of time divided by the voltage over the inductance, or in that case, multiplied by the inductance over the voltage. So in this case, it's going to equal the 10 amps times my inductance. In this case, I have to convert to Henry. So 64 times 10 to the negative 3 Henry over my 20 volts. And I get that it is something like 8.8 milliseconds. And that's going to be the case across the entire circuit. This is also 8.8 milliseconds. This is 8.8 milliseconds. 8.8 milliseconds. 8.8 milliseconds. Because I want you to think about all these inductors are working simultaneously to build the total current charge of 10 amps. Now that we have the total current, I can also start to fill in some other knowns. I know that the total current is equal to the current across the inductor, the first inductor. So this is 10 amps. I can then use that to figure out the voltage across 1. So I'm going to use this, our voltage equation here. So V1 equals L1 I1 over T1, which is just T1's always the same for everything. So I could just write T. That's going to then equal, I have to convert to henries, so 10 times 10 to the negative 3 henries, times my current of 10 amps over my time of 8.8 milliseconds, so 8 times 10 to the negative 3 seconds. Oop, it's a weird way to write that. There we go. And that's going to equal roughly, again with some rounding, like 11 point, we can say 36 volts. Now if I remember, I can then use the fact that I know my total voltage is equal to the voltage across 1 plus the voltage across 2 to figure out the voltage across 2, right? So if V total equals V1 plus V2, then V2 has to equal V total minus V1, which is going to give me 20 volts minus 11.36 volts. I get V2 equals something like 8.64 volts. 8.64 volts. I can then use that to figure out the current. So I of T equals V over LT. So in this case, I of 2, V2, L2, and then just time, right? Because it's the same. Is then going to be the 8.64 volts over my inductance across 2, which is 11 times 10 to the negative 3 Henry, times the time, 8.8 times 10 to the negative 3 seconds. Running out of room here, but you get the idea. I across 2 is then equal, you can keep the parenthesis of sub 2, it's just more notational preference than anything else. But we get that it is equal to 6.91 amps after some rounding. So 6.91 amps. I'm going to try and keep everything on the same page here, but I'm running out of room. We can then use kind of what we know about the rest of everything to figure out kind of our left unknowns. We know that I total equals I1, which is equal to I2 plus I3. So we know I3, write it right here. I3 is equal to I1 minus I2. So I3 equals, I'm just going to slowly write this in here. So 10 amps minus 6.91 amps. So I get I3 is equal to 3.01 amps. 3.09. 09 amps, not 01. I can add, I promise. And then we're going to calculate voltage across 3 using our same equation. So V3 equals L3 I3 over T, which is going to give me 12 times 10 to the negative 3 Henry. Multiplied by the 3.09 amps over the time of 8.8 times 10 to the negative 3 seconds. And I get that my voltage across 3 is something like 4.21 volts. So 4.21 volts. I then know that V2, right, V2 equals V3 plus V4. So V4 equals V2 minus V3, which is going to give me V4 equaling, I've got 8.64 volts. The table really helps organize all the data, right, because we're dealing with a lot of numbers here. We will get this all on one page. And then the 4.21 volts, and I get something like 4.43 volts. 4.3 volts. I'm going to leave just a little bit of room down here to calculate the final current, which I could then, honestly, actually I don't need to calculate anything, remembering that I3 equals I4, right? So this is also 3.09 amps, and I'm done. And again, if there are some minor discrepancies, it's because of rounding errors. We're dealing with very small numbers.